Okay, thanks everyone. I hope you all enjoyed your lunch, and I hope you've all had a tea or a coffee to get yourself pumped up for the afternoon. So to take us through the rest of our 7-step process today, we have Patrick Racine from Dubois, Canada, and he's going to introduce us to steps 3 and 4 before Bill joins us again. We will have another break at 2:30, and then Patsy's going to wrap us up on step 6 and 7 then, and then we're going to follow that up with a panel discussion. But for now, Patrick, if you can tell us a little bit about yourself, please join me in welcoming Patrick.
Thank you. When I saw that Patsy put me at the first lot after lunch, I wasn't sure if there was a compliment or an insult, but I'm going to do whatever I can to keep it interesting, knowing that we're on that little slump after lunch. My name is Patrick Racine. I'm with Dubois, Canada. Dubois is an industrial group that recently purchased a lot of water treatment companies. I spent my whole career with Cleansoid Canada and Elvin Water that just got recently purchased by Dubois, so you may have heard those names. I've been in the water treatment business, so my bias is I'm a water treater, and as I present this, I carry this bias that I want to declare. That's the perspective I have. I've been involved with ASHRAE 188 in the committee, not as long as Bill, but I joined, I believe it was in 2008, and I was there for the 7 years it took to finalize it. I'd like to claim I'm the one that brought it to the end. And my mandate when I went on 188 is I wouldn't consider myself a subject matter expert as much as I'm an engineer and I'm a practitioner, and I've seen how people use the standard in the field. And that's the voice I always try to have on the committee is, what would the user say if they saw that? And does that make sense for the user? So I'm not a microbiologist, and that's not my background. My background is making things work in the real world. So that's a perspective I have, and that's why this section I think is interesting. That's because to me, that's what I do, is I want to go in sites and identify risk. A couple of things during lunch, there was some good conversation. One that just happened is, didn't 188 just replace Guideline 12? And some people have heard of Guideline 12 and ASHRAE Standard 188, and actually they build on each other. ASHRAE 188 is the structure. It's the skeleton that holds the plan together. It's the how do you develop a plan. But what you do with the plan and the actions you take are actually part of the Guideline 12, that we're actively trying to finalize a new version right now. And that's what the meat of what you're going to do is. So as we talk about this, you may say, well, you're not telling us how to solve it. You're just telling us what to be worried about. But that's what 188 is. It's the skeleton of what do we need to consider. And then you need to go to scientifically backed ways of addressing those things. And Guideline 12 is an important tool. Guideline 12-2000, which hasn't been renewed since 2000, is actually still a very good document, but it definitely needs renewal. And we're hoping that we'll have a Guideline 12 2019 if everything goes right. And we're going to be able to bring better data to the front. Another thing that came in during lunch I think is important to bring is I'm a firm believer that the water management plan should have been called a water management program. And the plan is only one part of your program. If you can write an amazing plan in a binder, put it on a shelf, and it sits there and nothing does anything about it, you need a program. And the starting point of your program is the plan you're going to write. Once you form your team, like Bill talked about, and you develop the plan, you also need to have an ongoing program. So when Patsy's telling us to write document everything, that's part of the program, is you're administrating your plan. And when Jeff was talking about all of the things they do with the work order system, that's a program. So the plan tells you what to do. The program is executing it. So, and that's something I keep repeating to people. You can't just write the plan and then say you're done. The other thing you're going to see is that we are all, in our own ways, able to present the entire process. And you're going to see some repeats. So I'm glad that a lot of the slides I have were actually presented by subject matter expert, like Bill said. I think that justifies it. The fact that it's consistent tells you that. So I apologize for the duplication, but I think there's still some important lessons here. So the first step is, once you've developed the flow diagram of your building and you know what's happening with the water in the building, you need to then identify within that diagram where are the risk areas that you need to address. And that's that section of the plan, which is the analyzing the building risk. And the first thing, and I saw that quote already this morning, but every building is different. Every building is absolutely different. In fact, there's studies that have shown that because there was a language at one point in time that says that Legionella is everywhere. And if you look for it, you're going to find it. Well, Legionella can be everywhere, but it's not everywhere. About half of buildings, if you test them, will not have Legionella in it, but the other half will. And the two buildings from the outside could look identical, and one will be prone to Legionella and one won't. And there's a lot of factors inside the guts of the building that tell you that. So that's where analyzing the style of the building, the age of the building, the plumbing system, all of the hazards that are all the factors, in fact, hazards you need to be looking at within that building to understand your building. And that's where the cookie cutter approach to water safety does not work. You need to address it from the bottom, building the system, understanding that chain. And here we're not going to talk about the susceptible patient. We're not going to talk about the strain. In this section, we're talking about how do we block the transmission. So how do we minimize the risk of the transmission? So what device do we need to consider? And we've talked about this now. The other thing I am, besides a water treater, is I'm a hypochondriac. Any other hypochondriac in the room? You're not going to like me today. I'm going to tell you about everything you need to be scared about in this building here, and when you go back home. We talked about aerosolization. Well, where do you get most exposure to aerosolization in your life? Every one of us every day get to spray ourselves with a bunch of tiny water droplets that we're breathing thousands of during our shower. So obviously in a building where there's a risk, where will the greatest exposure be? It's going to be in showers. So that's one area that you need to identify if you're looking at your building. That's an area we need to consider. It doesn't mean that it's dangerous, but it means we need to consider it and be a part of the plan. So that's probably the most common one. The other one both in the hospitality business and in the healthcare business, a high risk area is pools and spas. If we looked at the temperature where bacteria prefer to grow, well, a hot tub running at 104 Fahrenheit is pretty much where you want to be if you're a bacteria. Aerated, bubbles, warm, sunlight, lots of biological food coming to you by baiters coming into that pool. And then as a user of the hot tub, you're sitting 3 or 4 inches from where the water is bubbling away with water droplets. So high exposure risk in a perfect environment for the bacteria to grow. So definitely, as you assess your building and your flow diagram, hot tubs is an area of critical importance. In fact, I believe the largest Legionella outbreak in the world, someone can correct me, but one of the largest one was in Europe, in the Netherlands, I think, in a home show where they had a hot tub on display and thousands of people walked by that hot tub during the trade show over the weekend. And it was in the 200, I think 278 is the number I have in my head. It's a high number of people that caught the disease from that one hot tub. So I still use hot tubs, but I worry when I'm in it, so I'm not relaxing. Spas and hot tub. The other one, we see these a little less in Canada because of the climate. When we need to do humidity control, typically it's in the winter, and especially in larger buildings, it's usually done with steam. And if you do steam humidification, you've actually reduced your risk because the bacteria doesn't live in steam. It's going to die almost instantly, not instantly, in steam. But then you go to other climates, warm climate, where you go down to Arizona for your golf vacation, and on the patio there's these humidifier to keep you cool and feel comfortable. I mean, those are Legionella spraying machine. If the pipe that goes to there is exposed to the sun all the way to that machine, that's a high risk device. The next one that is high exposure also are water features, water fountains that are put in places where we want them close to where public will go. You don't put a fountain where no one goes. You put a fountain where you want people to agglomerate around and think. And in fact, in healthcare facility, historically, we tended to put them in the high-risk population, the oncology department, as more of a meditative place where people could go and reflect and think. And we had the highest exposure of patient risk in a device that was causing potential risk. And there has been an outbreak associated with fountains and water features in healthcare environments. So one to consider as you're identifying the risk. Most healthcare facilities being built today will not have water features. Most water features have been turned into planters and rock gardens, and the water's been removed from it. But they're definitely a high-risk area when we look at things. The other one is sprinklers. And when people say sprinkler in a text, there's actually two things that come to mind when people start talking about sprinklers and aerosolization. There's a sprinkler head in this building that are for fire suppression, and then there's lawn sprinklers. And I never really know which one people want to address. But to me, from a risk management standpoint, these sprinkler, if they come on, how many people have been sprayed by a fire suppression sprinkler in their life? How many people have been sprayed by a lawn sprinkler in their life, right? So for what am I going to worry about? I'm going to worry about the lawn sprinkler. If these turn on, I'm glad they're going to turn on. And if I have a potential risk of catching a waterborne disease from it, I'm glad the building's not going to burn down. So that's, although it needs to be considered, that's not where I'm going to worry more. These lawn sprinklers are being used in times where the weather's warm and the pipes are underground. They're stagnant for probably 24 hours, maybe more, and they sit there stagnant, and then they turn on for a short amount of time, and whatever biofilm and bacteria grew in there is what's being exposed to the people walking by it on the lawns. And it's actually one of the areas that I've always wondered why it's actually not more studied. I don't know if we've actually really looked at that as potential sources and outbreaks. We don't talk about it, but to me, as an engineer and not a microbiologist, I'm like, this is probably, after cooling towers and showers, the place where we're going to have the most trouble, because everyone is exposed to those on a regular basis. Ice machines. It's funny, Google ice machine and everyone gets the same picture. But I use that picture for two reasons. In fact, I Googled dirty ice machine to do that. And that's the picture that came up. But it's disgusting. I wouldn't want to be a patient chewing on those ice cubes after surgery, like we talked about this morning. But there's also a message here of, it's not because it's dirty that there's Legionella in it, and it's not because it's clean that there's no Legionella in it. Legionella is not visible through the naked eye. So don't fool yourself that the hot tub's clean because I can see the bottom. Don't fool yourself that the cooling tower does not have Legionella issue because the water looks clear. If the machine was clean here, it could still be a risk. And why is ice machine a risk? We talked about the aspiration aspect, but from a mechanical engineering standpoint, what happens with an ice machine is you have a compressor at the back that runs your refrigerator to make ice. That compressor is basically taking heat out of the water and pushing it out through a fan. So you have a heat generation source sitting at the back of your ice machine. And because people don't like taste and odors in ice, we'll put a carbon filter there that removes taste and odor and chlorine. So there's no chlorine left in that water. So now you have water that is dechlorinated, that's sitting. And the other aspect, the third aspect, is the maintenance crew wants to be able to pull that machine off the wall to do some maintenance. So there's a long coil that goes to the connection to the wall so that we can pull the machine away. So now we have a residence time through the coil of warm water that's been dechlorinated to sit there, grow bacteria before we make ice with it. And if you look at that curve, you can say, well, at minus something degree, the bacteria won't grow. It won't grow, but if it grew in the coil, it won't die. And cold doesn't kill Legionella. High temperature can kill Legionella, but cold won't do it. So the ice is actually a perfect environment for the bacteria to survive, and the ice machine was the perfect place for it to grow. So another thing to be grossed out about next time you're drinking. Cooling tower. I love this picture. This is actually a colleague of mine, Dan Lodge, that's talking to one of our customers. I don't know if you can tell from the picture here what's hanging out the customer's mouth, but one of the risk factors is a smoker. So I just like the fact that this guy has a cigarette hanging out of his mouth as he's talking to us. Cooling towers are a high risk. They're the poster child for Legionella, mostly because, well, I mean, there's a lot of reasons. One is that the Philadelphia outbreak was linked to the cooling tower. Though you could say that they really test every other building water system that day in that hotel, and could the patient have gotten it from the showers? And it was identified in the cooling towers. And I've questioned people on that subject, and not everyone agrees that it had to be the cooling tower. They're also, the reason they're a problem is, by design, cooling towers spray water to increase the surface area so that water can evaporate. Water has this amazing ability. If you evaporate a pound of water, you grab 1,000 BTU from the rest of the water, and it leaves with the evaporated water. Evaporating water is a great way to remove heat from something. That's why we sweat, and then when our pore evaporate, we get cool. That's 1,000 BTU per pound happening. But to do that, you need to aerosolize it to the greatest surface area possible. and you need to blow air through it for the water to evaporate. So that's a perfect environment to spread things. Now, cooling towers are designed with drift eliminators, and when you see a cooling tower and you see a plume coming off of it, that's not the problem. The plume is evaporated, condensing water, and that's fine. It's the water droplets that would go through the drift eliminators that are your problem. And if you maintain them well, you can minimize risk. The problem with cooling towers is because of that aspect of spraying it around and pushing it with fans, it spreads to very, very far distances. There's been studies that have shown that these water drops can travel kilometers in the air before, and so they can spread to very, very far. So these cooling towers, when they're implicated in an outbreak, it's usually a large outbreak because it sprayed a lot of water to a large population. The Quebec City outbreak is a perfect example of that. But they're not the largest source of the disease. In fact, I believe that they're, depending on the statistics you look, they're more in like the 30% of the disease are from the cooling towers, while closer to 70% is from your domestic hot water system. The other types of cooling that we see, and they are different, though most uneducated people about the subject, they look the same. Evaporative condensers, those are used more in manufacturing facilities, food plant arenas, where you're actually cooling down ammonia in coils through an evaporative condensers. Very similar to a cooling tower. They have differences. They usually have a lot less water in them, so the residence time of the water is quicker, which makes water treatment challenges potentially more complicated and can lead to the bacteria growth and coming out of control limits quicker. So important to consider. And if you weren't scared yet, medical device. Medical devices are an issue. So next time you're seeing a dentist and they're spraying your stuff, maybe you want to ask them what they do as far as cleaning the tubes and all the water, and they probably have a carbon filter on that line so that the stuff they're spraying you doesn't taste bad and doesn't have chlorine in it. So medical devices have been associated with Legionella, and that's something, as you do your risk assessment of your building, you need to look at, do we have these medical devices to consider? So is it the all-inclusive list? It's not the all-inclusive list. In the end, it's what water system can create a path to exposure. What water system could create aerosolization? Here I'm talking more of a healthcare, a hospitality environment. If you're in an industrial plant and your machine cooling has quick connects and operators are disconnecting hoses and they spray, when those are all high exposure area, there's been outbreaks in automotive plants because of that. So you need to have someone that, like Bill said, understands your water systems, but also understands what could be a risk factor within your building water system to do a proper walkthrough of the facility to understand it. We've talked about it. Keep hot, keep cold. There's a growth decline zone. This graph, I need to change in that slide. I'm not a big fan of it because someone could say that by the time you're at 113 Fahrenheit, you're actually in a safer zone, and that's not true. A domestic hot water system should be kept as hot as possible. The federal government's talking about 60 degrees, which would be about 150, I think, 140. So that's a much higher temperature. But what happens is, in healthcare facility, people are scared of scalding. In senior living facilities, people are concerned of scalding. And then they lower the temperature. The energy engineer on site is trying to lower your domestic hot water temperature, and that recirculating loop is now running at the perfect temperature for bacteria to grow. So there is this water energy healthcare nexus that we need to come up with the right solution where the goals of your lead building absolutely go against the health prevention. And there's a strong conflict there. And then we need to decide, are we ready to consume a little more water and energy to protect the people that use the building and look for those efficiency gains somewhere else? The other thing I think was touched on, but is super critical, the National Science Foundation says that the number one culprit is the biofilm. The biofilm is where the bacteria grows. Legionella bacteria will want to find. Can you guys hear me? Is that, yeah, perfect. That's much more pleasant. The biofilm is where the bacteria grows. It harbors itself. It's protected from the disinfectant in the loop, and it can live there, grow, multiply, and then there's going to be a disruption to the biofilm. It'll fluff off, and within that biofilm is this microbiome of all sorts of bacteria growing and feeding on each other. So biofilm is what we need to think about when we're thinking about risk mitigation and finding where the biofilm can exist. And the biofilm can exist, and this is an interesting group where we've got healthcare people, we got a lot of water supply people. The biofilm exists through the entire process. It exists in the water source when you walk down in a lake or a river and that rock's a little slippery from the slime on it. That's the biofilm where bacteria are growing. And then it goes to your filtration system, and the biofilm will exist within sand filtration, media filtration system, where the bacteria can actually harbor itself within that. And even if you have the right disinfectant level outside of the biofilm, it may not attack it properly. It will exist in the storage facilities where biofilm will form on the wall. And it will definitely exist throughout all the pipes within the network. So that's on the upstream side of the meter. But if we go back to Bill's diagram from the CDC, that what happens in the building is once you've done that plan that Bill was talking about, is you need to go to the next step and say, okay, now that I understand what the plan of the building looks like, the flow diagram of this building, and I understand all the devices I need to consider, let's look at, and the fonts are a little small here, but let's look at where the risks are. That green logo is the temperature, and then there's stagnation, no disinfectant, condition where aerosolization can happen, and then you go through the diagram and say, well, there could be disruption in the municipal water supply that causes risk. There could be a gray water situation. There could be a drop in pressure. There could be flooding in Montreal that causes the water plant to may not be able to keep fully with the treatment. There could be construction down the road where there was water infiltrating into my network. Understanding that is a risk factor when the building owner needs to assess their building. And they need to think about that as they think about the management plan we're going to talk about. And then you look into more of the cold water distribution system where there's a lot more to start thinking about. In your cooling tower, obviously, you're concerned about aerosolization. You're concerned about the disinfectant level within the cooling tower, the temperature. I'll talk about a study we've done with some Quebec data where temperature is one of the strongest leading indicator of future positivity in cooling towers. And cooling towers that run at a higher temperature are much more prone to have Legionella in it. And cooling towers that are properly designed and running at lower temperature have a much lower risk of Legionella. And you go through each of these machines, the ice machines, the decorative fountains, the pools, the hot tubs, the shower, and you identify the potential risk area so that as a team, you can decide where do we need to focus our plan on. And we'll do the same thing with the hot water system. Hot water system, mostly temperature, unless you have other problem and you're looking at secondary disinfection. We'll talk about that. But the temperature, is your supply and return temperature almost the same, or is there's a huge delta between your supply and your return? If there's a large delta, you probably got some flow issues that you need to consider. And you're increasing your risk because of flow issues and temperature issues all of a sudden. So understanding that picture of your building and the risk is what we're doing here. Same thing on the exit from the building. So as you do your whole plan, you end up with a map of where we need to think about having control measures and the verification and validation steps. So as we look at a summary of this, you want to identify the risk area, and then you're going to establish control measures and strategies, which was the next section here. How do we come up with control measures and strategies for this section? We want to use the flow diagram that we did in step 3 to decide where we need to focus our attention. And then we're going to determine what control measures and where they are. We're going to consider areas where there's vulnerable occupant as higher risk. The same shower in a neonatal part of the hospital is a much higher risk than in the gym of the staff. Not that we don't care about the staff, but the risk is different. So we need to understand the population that's exposed to it. And then include provision, and this is where the conversation with the utilities become important, is if there's water service disruption, how do we respond to them? But these water service disruption, I'm going to do a little caveat because we do a lot of work in Southeast Michigan and in the Flint area. And last summer, in our customer base, there was a huge spike in the presence of Legionella in every building in Southeast Michigan that we tested. And it's not because the buildings all of a sudden all decided to run differently. something was happening in the water distribution system in Southeast Michigan last summer, because we saw the spike everywhere. It wasn't a one-up. So these disruption, and that's where, if the conversation is happening both ways between the building and the distribution people, we can start having a more meaningful conversation. I believe that we need to get to the point where there's better data. As the buildings collect this data, they should be somehow feeding it back to a network, so that if we see early signs of spike somewhere, as a partner, we can work together and say, hey, we're seeing this Legionella popping up high in all these buildings in our network. Maybe something's happening that we've changed, and we can start drawing conclusions that conditions change within our distribution system that caused that spike to potentially happen. And that's a shared ownership. And this morning we were talking about the utilities being the champion of water safety and pushing their customers to have water management plan. To me, that's an important part of minimizing the liability portion of a distribution, a supply company, is letting them know, hey, we're supplying you this water, this quality, but once it crosses the meter, you should be thinking about these things, because you're not using the water necessarily like it was designed to be used. If you look at a university campus and you're supplying them, 8-10 million gallons a day of water, of that water, 7 is being used for space cooling, but you're treating it to be potable. So they're using it for a different use than what you've treated it to be. So that conversation needs to happen. And that's all part of managing the risks. And for Patsy, document everything. and we're going to talk about that more. And in fact, I think that's an important part of it. The solution to document is to have the right tools in place to document it. The paper logbook is probably not the 2019 solution to document. There are tools out there that will allow you to document things better and react and identify trends and let you know that things are happening before you realize they're actually happening. So we've identified what we need to be scared about. Let's look at the more fun stuff, is how do we protect ourselves? How do we control these risks? What kind of strategies do we put in place in buildings to talk about that? And you've talked about it this morning. There's a lot of strategies. And those strategies is that fourth part of the ASHRAE 188 section. And those control measures that you're going to put in place really should follow these 4 steps. Is one, you need to set control limits that are set for each control point. What does in control mean? So that we can then decide, well, if that's the limit, how do we monitor for it? So we start monitoring, make sure that we're within the control limit. Then we need to know, how often do we do it? Is it the total bacteria count weekly, the Legionella monthly? What are the frequency? We need to define that as part of our plan. And then before you do any kind of sampling and controlling, you should know how you're going to react to the results. Users are getting better, but I remember 5-6 years ago, customers would ask us to test for Legionella, but they would have no knowledge of what control limits they were trying to achieve, what reactions they were going to do once they got the results. So you need to establish that before you test. So again, a little bit of repeat here. Keep hot, keep cold. That's the best thing you can do to mitigate the risk of bacteria growing. Prevent water from not flowing. What's your touchdown? Touchdown for you, right? So we want the flow, the for you, right? And we want to make sure there's enough disinfectant, if disinfectant is part of the control measure. And then have the right practices in place to minimize biofilm, scale, corrosion. The scale and the corrosion, the issue is that's where the biofilm will stick. That's where the bacteria is going to go hide. You can have great disinfectant in the bulk water, but the scale and corrosion are cracks and crevices where the bacteria can decide to set itself to grow and become bigger. So what I'm going to do here is I can't, in this level, of course, go through every single system and every detail, but I took at a high level 2 of the main systems that exist in almost all large buildings and say, well, what kind of control measures would you look at in a domestic water system, so the potable water loop within the building, and then we're going to look at the cooling towers and the evaporative condensers after. So in a in a domestic water system, you want to make sure that the recirculating water loop is at the right temperature. boat supply and return, like I mentioned before, that an increasing delta is a flag that something's happening. You want to make sure that it's recirculating, that it's not stagnant. And this water aging, a lot of us have talked about it today, and it's a concept that's actually, to me, very, very critical. And we talked about the plumbing line size, right? This building was built, I don't know, I'm looking at the brick, it's probably built in 1974, is my guess, based on the brick that's in here. At that time, the faucets were running a lot faster. The towers were flushing a lot more water per flush. If you go to a healthcare facility, the patient room had 4 beds, 1 sink, 1 toilet. And so today we're building the hospital where there's 1 bed, a physician sink, a patient sink, a bathroom, and a shower. So we got 4 fixtures for 1 patient, where we used to have 2 fixtures for 4 patients. So but then the plumbing code tells us, well, based on the number of fixtures, this is the diameter of pipe I need to put into the building to supply all these fixtures. So now we have high efficiency fixtures that use less flow per fixture. We have a higher fixture count. And so we're putting huge pipes in our building that are increasing the water age. Someone said 100 days. Like that's crazy. So we are causing, by gaining efficiencies, but not evolving our code, we're causing this water to age. And there's no way the disinfectant residual is going to last 100 days in that building, especially in a hot water recirculating loop, because that's what's happening in that hospital. For people that aren't familiar with the domestic hot water system in a large building, is it's recirculating. You don't need to flush all the water from the hot water tank like you do in your house and wait till it gets hot at the sink. The water is flowing through that building hot all the time, and you're just drawing off that hot water loop. So you're only displacing the little bit of pipe that's between the recirculating loop and the faucet. But that water is recirculating, so it's gaining age as it's recirculating. If we're drawing less hot water, if we're returning our patients home at the end of the day and they don't stay overnight and they don't use a shower, and that shower is part of the fixture count to decide how big the network is, then our water is recirculating hot, but no one's using it. And then it's getting older, the disinfectant level is dropping, and bacteria can start growing. So on the domestic front, we need to consider that. The cold water, and I wrote the Canadian reality, is I think we need to worry less about the cold water domestic side than the hot water domestic in the building water system. For one, it's not recirculating, so the water age will be lower, and it's also stays colder. Now, if you operate a building in Phoenix, the cold water coming from the city is actually not cold; it's kind of tepid. So it's already in that prime temperature to grow bacteria. So it's a higher risk on that. And then the filtration media is something we need to consider when we look at a control measure. And the filtration media, both if you decide to filter the water coming into the building, realize that that's now a container where bacteria can grow. And the type of filtration you decide to use is important then. And also we're going to talk about point of use filtration as a potential risk reduction measures in high risk population. So I have a slide here about secondary disinfection, which is actually it used to be more common in the US. The people that are facility people, you've probably heard of a copper silver deionization, monochloramine, chlorine dioxide, all those technologies to support killing bacteria in the water. There's a lot of really, really good salespeople that are going to engineering firm and recommending that all buildings be designed with these units on it, whether or not the building has a risk profile to need it. And I speak as someone that sells all of those technologies, but they should only be used if they're needed. Because if you start using them, you've opened a Pandora's box, and then you could never be the one that decides to turn it off, because who holds the reliability of turning off a device that was designed by the design engineer if something does go wrong in the future, yet it might not be needed for your building. So it should only be used if the water management plan and the program establishes that you should have that device in your system. Don't fall prey to just buying a device because it sounds like a good protection insurance policy. That's my personal opinion here. And in fact, your water management plan is the case for everything else you do. This is your roadmap for making decision within your building on how to make the proper risk mitigation decision for your patient population or your occupants. So what are the choices? The first one's actually not secondary disinfection, but it's temperature. Control the temperature below 77 or above 140. If you do that, you're really mitigating the risk of bacteria growing in your system. That's the first step. From a temperature standpoint, there's also using temperature as a corrective measure to clean a system. I'm avoiding the word sterilize because hot water flushes tend to be fairly ineffective in controlling it. They can achieve results very quickly, but the bacteria tends to come back in studies that show that they will come back very, very quickly after. So just using temperature, if you have a problem, tends to be a poor selection from our experience. It's also, depending on the design of the building, can be very damaging to your building because to bring the temperature to 70 C, all of the gaskets and seats and all of your plumbing fixtures were not designed to handle those kinds of temperature. So you're risking your entire equipment based on that. Then there's the secondary disinfection option, again, only if you need it. But the secondary disinfection option of going with chlorine, chlorine dioxide, monochloramine, and I'm not going to go into which one is the right one and the wrong one. They're all right and they're all wrong. It depends on your building, it depends on your application, and you need to deal with someone that can educate you on making the right decision for your building. There's also copper silver ionization, which is an effective way to control the bacteria, which is also a choice that has its benefit and its drawback compared to the oxidization solution. And then there's point-of-use filtration, which is an interesting solution for healthcare facilities in high-risk population, both as a reactive measure, definitely a great solution as a reactive measure, but also a potential good solution in a very high-risk area. Because although these bacteria are very small, I mean, they're a cylinder like that little toy you got, but their diameter is a 0.2 micron diameter. So it's a small bacteria, 0.3 micron. So you can actually, in the market right now, buy filters that will filter to 0.2 micron and actually filter out bacteria. And but you need to choose the right size filter. It needs to be 0.2 micron to do it, and it needs to be proven. We're actually in the process. I'm part of this study that's being peer reviewed right now. It's a study that was done at a healthcare facility here in Ontario, where we proved the efficacy of these kinds of filters. And it's the only technology, and again, I'm not promoting it per se, but it's the only thing in all the research that's been done on Legionella. It's the only thing that every research paper that's published, any kind of filtration, it filters all of them. There's never been, you can't say it protects 100%, but there's never been Legionella measured downstream of that filter in all the studies that have been done out there. So, but there's drawbacks to that. There's drawback. It's not easy to manage these filters depending on the manufacturers. They're now better. It used to be 7 days, I think, the first version, but now they're 30, 60, and 90 days. So there's longer life, but it's still, you need to change these filters on a regular basis. If there's any water disruption and there's sediment in your water, these are 0.2 micron filter, they'll plug up instantly. So there's a management issue with managing that, and they're not cheap. So there's a cost to it. But they're not cheap. But if you're thinking of a healthcare facility, the cost of turning over a room and sterilizing it and cleaning it to add $1 a day, which is really about what it costs in these filters, is not cost prohibitive in a healthcare environment. It's not the only solution, but it's actually a very good solution, especially in a case where the building's been identified to have a lot of bacteria in it, and we don't want to evacuate the building occupant. We can put these filters and protect them. So on the domestic side, that's an interesting solution. But again, costly management, labor issues to swap them. So those are some of the strategies that we can implement. These are not all the strategies. I'm looking at a high level. Once you've identified the risk, what can we do? On the cooling towers and the evaporative condensers, again, something that almost all buildings have. What are the things you need to look at? Well, you should have the right water treatment program with the right partner, and it should use automation. There's the CDC produces, this is a really good Saturday morning reading, the Morbidity and Mortality Weekly Report, MMRWR. You can read that every Saturday morning. CDC publishes it if you're interested. But they did a study that showed that usually when there's an outbreak, more than one thing went wrong, but the absence of automation is a huge source of cooling tower issues because the biocide was the person that sold you the drum of biocide, they sold you a good biocide. It wasn't at the right rate in the right place at the right time. You didn't have the right dosage of biocide in your water. Automation is what takes care of that. A lot of the issues with cooling towers is they go stagnant, and because there's poor automation, the timer, which was a Christmas light timer, that turned the biocide pump, turned it on when the system wasn't running, and then it didn't add the biocide to the system, so the system didn't get exposed to that. And it sounds simple, but sadly enough in our industry, it seems like that's the last place people will automate things and improve things. So automation is biocide feed and biodispersion is really important. Have your staff engaged in the program. They should test the water regularly as clean as possible. It's going to reduce how much biocides you need in your system, and it's going to keep the surfaces cleaner, which is less area for the bacteria to harbor itself and grow. Minimize stagnation, minimize deadling. We talked about that. If your cooling tower, I mean, this spring has been a very cold spring here in the GTA. Cooling towers turn on today because it's a warm, sunny day, but they might be off for 3 days. I mean, it's a long weekend. The odds are it's going to be cold all weekend. So the cooling towers are probably going to sit idle for 4 days. Bacteria will grow in there, and then the system will kick back on automatically, especially in this building where a lot of the heat is from the occupants. So the building load, the cooling load on the building is going to be a lot lower this weekend. So cooling towers may not run all weekend, and then they're going to kick on Monday morning when it's sunny, or Tuesday morning next week when it's sunny and all the population comes back in. Well, that system has been sitting idle, that's not good. So it doesn't mean you need to drain your system for the weekend. That's not practical. But there's good practices of automating your recirculating pumps on your system that they kick on and you recirculate that water and not let it sit stagnant. If you can afford to take that second cooling tower completely offline, that's great. If the design of the building, especially in data centers and large buildings like this, they throttle on and off, make sure that they recirculate. That's an important step. Physical cleaning of the system, and then sanitization. There's some good kits out there where very easily you can do at least twice a year sanitize your cooling towers to make sure that you've cleaned it and got a bit of shock to it on top of the regular water treatment programs. And then the maintenance, make sure the drift eliminators are in good shape, the wet decks and the distribution tables are clean, that the fans is turning well. Those are all good steps. And then test for Legionella on a regular basis. And that's important. And I'll talk about in the next slide about a study we did in Quebec, where in Quebec they mandated testing of cooling towers every 30 days. And it in our mind, because we treat a lot of cooling towers in Quebec, if you were to ask me how well we were doing treating cooling towers in Quebec, I would have told you we don't really have a Legionella problem. We do some sporadic tests. Some of our customers ask us to test. Whenever we test those customers, results are pretty good compared to the studies I've seen out there. Our results are pretty good. But that's a biased data set, because if you're selectively choosing to test, you're already a proactive thinker that's engaged in your cooling tower management program. You probably have a great automation system. You probably have operators that test the water weekly. You're probably doing total bacteria counts with FIT slides every week. So are you going to get better results when you test for Legionella? Probably. So it's a biased data set. And I had my blinders on. We published a paper with ASHRAE last January on the data in Quebec. We had over 300 cooling tower, over 100,000 data point in the study that looked at what are the leading indicator. Because of the Quebec study, what's interesting in there is we have engineers on site once a month doing water quality tests in the same database that we have Legionella results. And we were able to draw some conclusion on what are the causality of positivity in cooling towers based on results. And whatever, I can geek out about this stuff, but the challenge of all the studies to date on Legionella and cooling towers is that someone would grab a water sample, test it for Legionella, and that same day grab a water sample and test it for water quality, and try to draw a conclusion based on those two samples. But the bacteria didn't appear in the cooling tower that day. The bacteria grew over time. There's a storyline to why the bacteria came here, and our study shows that it's usually 60 to 90 days before the high count that something went wrong. And that's something, you can't look at it today, you need to look at what happened over time, which would put a conclusion that you need consistent results all the time to get great results. And you can see that by keeping people accountable, by making them aware, it drove our Legionella positivity for 20% of our cooling towers were positive, which was mind-boggling to me because I thought we were doing good work. And 20% of the cooling tower had more than 10 CFU per mil or 10,000 CFU per liters. And over time, by awareness, we dropped that down to 6%. And 20%, 20 to 25%, a lot of studies out there show that that's what the average cooling tower positivity is. That's just normal. But when you force people to be aware and accountable and take action based on a very clear plan, the results improve. And this is with 3.5-year, 323 cooling towers, 100,000 data points. So it takes a lot of the noise out, and it shows that making people aware makes a big difference. So I'm a big fan of regulation. I'm not a big fan of localized regulation. So if we're going to do regulation, and that's why ASHRAE is doing a lot of good work, is let's create a regulation or a federal regulation that's all encompassing, that it says this is the bar that we expect people to do. It improves results, and the Quebec study showed that. A lot of data I talked about, you're going to get a slide. There's a good resource library. Aquanetics.com has all sorts of good best practices for Legionella risk mitigation on cooling towers, so that's a good place to go look at stuff. All those downloads are free. Just a quick conclusion, and we're going to have a bit of time for questions if we have to, or we'll move back to Bill, right? So set the control limit, understand what you're going to need to monitor, how often you're going to monitor it, and how you're going to react. And use an industrial hygiene detection approach. If you can eliminate. That's a better thing to do. If you can eliminate that's what's causing the aerosolization, eliminate it. If you can substitute it with a new technology, substitute it. And then start putting engineering control, and then start putting administrative control. And the last resort is that PPE. So like that point of use filtration is like PPE. That should be the last resort when you've done everything else. So if you could eliminate things that don't need to be used, then eliminate them, and that's going to reduce your risk. So after you do your survey and you have the whole building plan in front of you, don't just accept it as status quo. Think about all these risk areas and say, are there things like a water feature in a high-risk population area? Can we afford to get rid of that water feature? Absolutely. Instead of putting a stringent water treatment program on that water feature, let's consider the fact that we shouldn't have a water feature there and remove it. You've done a lot more to protect the population than put in an expensive treatment program on that one small water feature. So that's an important step as you do that. So with that, I'll pass it straight back to you, and we'll wait questions, or do you want to just... Is there questions now on this section? I'd be happy to answer questions, or we can move back to Bill.